So now we're going to begin section 6.4, graphs of logarithmic functions. We've been talking about these functions, but we haven't actually sketched the graph of a logarithmic function yet, and that's what we will do in this section. So recall the graph of an exponential function. I picked one example here, f of x equals 2 to the x. And yet we've seen this same shape for many different situations, right? Whenever the base is greater than 1, we're going to get this shape of a graph. And so what we want to do is graph the inverse of 2 to the x, which is f inverse of x equals log base 2 of x. And because it's the inverse of 2 to the x, I can take points on the graph of 2 to the x and just interchange the coordinates to get points on the graph of the inverse. Now I put 8, 3 here, but if you look, 2, 4 on the graph of 2 to the x will become 4, 2. 1, 2 becomes 2, 1. 0, 1 becomes 1, 0. Negative 1, 1/2 will become the point 1/2, negative 1. Negative 2 1/4 becomes 1/4, negative 2. I guess I also included 8, 3 because I know when 2 is 3, 2 to the third power is 8. So when I interchange the coordinates for that point, I'll get 8, 3. So let's go ahead and plot the. Actually, before I plot these, I want to say you really should have an idea what the shape is even before we plot those points, because we talked about how if you take the graph of a function, so here's kind of the general shape of an exponential function, and if I interchange the axes, the x and y axis, which the only way I can do that is I have to turn my piece of paper over, and so that the old y points sideways, the old x points up, I'm going to get the graph of a logarithmic function. So I get this shape is what we should see when we plot these points. And just before I put this sheet aside, the exponential function has a horizontal asymptote along the x-axis. When we interchange x and y to get the logarithmic function graph, that horizontal asymptote becomes a vertical asymptote on the graph of a logarithmic function. So here, let's go ahead and plot our points now. 8, 3, 4, 2, 2, 1, 1, 0. So there's this portion of the graph that does that. It goes on and on and on. But then we have 1/2, negative 1, 1/4, negative 2. And I think you can see, I could plot more, but this graph is just going to go plunging down along that y-axis. So for the logarithmic function, its domain is going to be the interval from 0 to infinity with 0 not included. That's the same as the corresponding range of an exponential function. The range of a logarithmic function is all real numbers, and that corresponds to the domain of an exponential function whose domain is also all real numbers. So just notice, I think we want to write down here that the y-axis is a vertical asymptote on the graph of a log function, and also notice that there is no y-intercept because x equals 0 is not in the domain. Also, there are no points left of the y-axis. So this log function graph exists only to the right of the y-axis. Let's try to sum these ideas up now. And here I have sketched just sort of the general shape. So instead of looking at one particular base, we're talking about any base b where b is greater than 1. We're only going to look at log functions where the base is greater than 1. And the shape will always look pretty much like so. The y-axis is always going to be a vertical asymptote. The x-intercept is going to be at 1, 0, no matter what the base is, because log base b of 1 equals 0 for any base at all. As x approaches infinity, f of x approaches infinity. So this graph, there's no horizontal asymptote here. This graph just keeps rising and rising off to the right. As x approaches 0 from the right, f of x approaches minus infinity. That means as we get closer and closer to the x equals 0 or the y-axis to the right of it, this graph goes plunging downward to more and more negative values. There is no y-intercept, and there are no points when x is less than 0. Again, I mentioned the domain and the range. And then I just put in quotes here log functions. You know, people always abbreviate the word logarithm or logarithmic with just log, log. So let's do some exercises now where we're going to sketch some graphs of log functions. First example I have here is f of x equals log of x. Log of x means log base 10, right? I'm just drawing my axes. So maybe it's worth noting here, this is log base 10 of x. And just what the main thing you have to know is that for any base at all, if the base is greater than 1, we're going to draw this shape. So I'm not even going to have to plot many points here. I'm just drawing that shape. The x-intercept will always be 1, 0, no matter what the base is. And make sure you draw your graph approaching the y-axis and plunging downward so we can see that there's a vertical asymptote there. There's no y-intercept, so that's all we have to draw. For the second example here, f of x equals ln of x. Now ln of x means the same thing as log base e of x. The points are not going to be in exactly the same spot, but the shape is going to be the same. So all you have to do is get the general shape. You don't have to plot a lot of points. The one point that will be in exactly the same position is 1, 0. Because that always, log of 1 is always 0, no matter what the base. And again, they're not the same graph. We could plot more points more accurately, but I think the main gist of this is to know that the general shapes of these two are really very, very similar. Okay, let's do some more. Okay, number 3 here is, okay, log base 2 of x minus 3. Now we got something going on here because we see that we're subtracting 3 inside parentheses. There's a transformation going on here. We have a horizontal shift, right? Of 3 units to the right in the positive direction. So let's think about how that would affect our graph. we think back to our general shape, if we shift the whole graph 3 units to the right, this point at 1, 0 is going to move over to 2, 3, 4, 0, right? The point at 1, 0 will now be right there. And, you know, I'd say even more important than getting that point correct is that when we shift horizontally, the vertical asymptote moves along with the shift of the graph. So we had a vertical asymptote at the y-axis. When we shift 1, 2, 3 units over, we're now going to have a vertical asymptote right here. Now that's a vertical line. That's the vertical line x equals 3. X equals 3 is the vertical asymptote. You have to get this labeled. So that's just a key to being able to draw the graph. The x-intercept is 1 unit over from that asymptote. So we're very close to the asymptote to the left of that x-intercept, plunging downward. We turn the corner, kind of take off, and there's my shape. So this x-intercept is actually the point 4, 0. But again, I'd say even more important, most important of all, is getting that x-intercept correctly. I won't ask you to state the domain, but I just want you to realize here the domain is actually going to be the interval from 3 to infinity with 3 not included. So the domain is affected by this horizontal shift. There are no points between the y-axis and the vertical asymptote, no points to the left of the y-axis. All right, number 4. So another transformation in number 4, and I think you remember when you add outside the function that it's a vertical shift. Now, there's a convention in notation that sometimes people might say, well, how do you know the 3 is outside? It's always understood that there's grouping around that log base 2 of x. The plus 3 is outside of that unless there's other parentheses like we had in example number 3. So it should be clear from the notation. You could always write the parentheses if that makes things clear. I think in typography in a textbook, I don't think there's going to be an issue, but just be aware it's understood if there are no parentheses that the log base 2 of x is grouped with the 3 outside. So a vertical shift upward of 3 units, right? We're shifting up. So if I'm shifting up, maybe I'll make my horizontal axis a little bit lower. Now, you know, I talked about how the vertical asymptote was so important in number 3. In number 4, if we shift a graph vertically upward, the vertical asymptote moves upward also, but notice it just stays in its same position. So this vertical shift does not change the asymptote. X equals 0, meaning the y-axis is the vertical asymptote. My point at 1, 0, my old x-intercept is going to shift upward 4 units. I'm going to have a graph. Well, I guess I didn't give myself enough room. I'm going to just write over the top of myself here. Go around the corner and take off. So with the vertical shift, notice you don't really notice the change in shape that much. It's much less evident than the change from a horizontal shift. There's still no y-intercept. By the way, the domain here is not affected by this vertical shift. The domain is still 0 to infinity, with 0 not included. What about that x-intercept value? Is there a way we could find that? And I haven't given myself much room to write here, but if you wanted to find the x-intercept, we got to set the function equal to 0. 0 equals log base 2 of x plus 3. You would want to isolate the log. So negative 3 is log base 2 of x. Translate to exponential. 2 to the negative 3 power is x. 2 to the negative 3 is just 1/8 is x. So this point here, the x-intercept, is going to be 1/8 0. So we can find that point. We know enough now about how to work with logs to be able to, and we're going to, as we move further into this chapter, we'll be able to find more and more of these tricky x-intercept points. Okay. 2 more examples down here, number 5 and number 6. Minus log x, so there's no subscript. That means minus log base 10 of x. The issue here is really, what does it mean when we multiply by or -1, or when we take a minus outside the front of a function? That takes us back a little bit to our discussion of transformations. Minus sign in front means we have to reflect through, do you remember, the x-axis. And so what I might do here is I'm just going to, in pencil, I'm going to lightly, hope that shows up. That's not my answer, but that's our original log graph. Say it could be log x before the minus sign. And then when we reflect, the x-axis, the x-intercept will stay in the same spot. The asymptote stays in the same spot, but now we're going to be coming down from above and turning the corner going that way. I'm going to take my pencil mark away a little bit. Even though it's okay to leave that as long as it's clear what your final graph is. So we still have the point 1, 0, but we have this graph that actually goes off to minus infinity as x gets very, very large, and it approaches the vertical asymptote upward as x approaches 0. So that's a reflection through the x-axis. Number 6, we have a minus x inside the log function. So that's also a reflection, but a different kind of reflection. When we did our transformations, we figured out that minus inside means that we should reflect through the y-axis. So again, I'm going to just draw lightly, well, lightly or not so lightly in pencil, this sketch. And now that's not what I want. What I want is a reflection through the y-axis. Here the x-intercept is going to move from 1, 0. It's actually going to end up at -1, 0. And there's going to be a portion of the graph coming down to the y-axis on this side. Then we're going to kind of take off in that negative direction. That's the reflection of the basic log graph through the y-axis. And just from the graph here, I can see there's been a change in the domain, right? The domain of this transformed function. Just from what I've drawn, I see negative values of x are fine, all the way up to 0. 0 is not included, no positive x values are included. All right, so that's actually the end of 6.4.